Hello, my name is Debbie, and in this video, I will walk through I will walk you through my project, focusing on the full modeling process, from understanding the data to training models and finally evaluating performance on unseen data. I worked with prostate cancer gene expression dataset, which contains 79 observation and 500 predictors. This is a highly dimensional setting where the number of predictors is far larger than the sample size, making overfitting a central concern. The response variable is binary, indicating cancer versus non-cancer status, and the class are approximately balanced, which allows standard performance measures to be used without adjustment. Before fitting the model, I begin by assessing whether there is meaningful signal in the data. And to do this, I applied the Kruskal-Wallis statistics test to each gene. This is a non-parametric test that compares distribution across groups and is well suited to small sample, high-dimensional data where normality assumptions are questionable. The goal here is not prediction, but to understand whether individual predictors show marginal separation between cancer and non-cancer cases. The result shows a clear contrast between top-ranked and bottom-ranked genes. The box plot of the top-ranked genes show distinct medians and limited overlap between the classes, indicating strong univariate discriminative power. The opposite is true for the bottom-ranked genes, as we can see from this one. When we look briefly at the heat map I created, we see that many of the predictors are highly correlated, which reinforces the idea that the effective information content is much lower than the raw dimensionality. This further increases the risk of overfitting when flexible models are used without regularization. I then moved to model training and comparison. I fit 6 classification models, including nearest neighbor methods and classification trees, and evaluate their behavior using ROC curves. On the training data, highly flexible models perform extremely well. The one nearest neighbor here, as you can see on the ROC curve, achieved an AUC of 1, meaning perfect discrimination, and the unpruned classification tree with complexity parameter of 0 also shows near perfect performance. However, these models achieved this by effectively memorizing the training data. In contrast, more generalized model perform differently, like the 9NN, 9 nearest neighbor model, smooths decision boundary by averaging more neighbors, and then by averaging more neighbors. The 9NN is here, and the pruned trees with complexity parameter equal to 1 to 0.1 is much shallower, using fewer splits and fewer genes. On the training ROC curves, these models show slightly lower AUC values, but their behavior is more realistic and less indicative of overfitting. The most important results came from evaluating performance on unseen data. When the tests replicated holdout samples and the highly flexible models, particularly the 1NN and the unpruned tree, exhibited high test errors and substantial variability across replications.